Hello and welcome to Module 5B, the second part of the chemical quantities modules. This one is on moles. We have a solution on the right side here of 2 moles per liter. Liter beaker with 2 moles in it. We often talk in daily life about how many items there are of a particular sample. In this particular unit, we'll be talking about how many atoms. If we talk about eggs, we talk about dozens of eggs. A dozen eggs being 12 eggs. So that would mean a dozen atoms is 12 atoms. A gross is a quantity that's actually a dozen dozens. If you had a gross of bottle rockets, it would be 144 rockets. So a gross of atoms would be 144 atoms. Paper is sold in packages called reams of paper. A ream of paper is 500 sheets. So a ream of atoms would be 500 atoms. Case of soda is 24 cans, so a case of atoms would be 24 atoms. Deck of cards has 52 cards, so a deck of atoms would be 52 atoms. A baker's dozen of donuts is actually 13, since a baker throws in an extra. So a baker's dozen of atoms would be 13 atoms. So what word and how many does the chemist use as their version of dozen? The chemist uses a word called mole. A mole contains Avogadro's number of items. So a chemist's dozen of M&Ms would be a mole of M&Ms, and it would equal 6.02 times 10 to the 23rd M&Ms. Chemist's dozen of atoms would be a mole of atoms and would be 6.02 times 10 to the 23rd atoms, Avogadro's number of atoms. So that's your definition of the mole. 6.02 times 10 to the 23rd items is a mole. So let's look at it again. What if you don't have exactly 1 dozen? What if you have 2 dozens? That would be 2 times 12, right? 24 eggs. 3 dozen would be 3 times 12, or 36 eggs. 4.5 dozen, 54 eggs. 2 moles is 2 times 6.02 times 10 to the 23rd, or 1.204 times 10 to the 24th eggs. 2.7 moles, 2.7 times 6.02 times 10 to the 23rd is 1.625 times 10 to the 24th eggs. If I'm converting moles to atoms, let's say I want to know how many copper atoms are in half a mole of copper. I use my conversion factor label technique. 0.50 moles times 6.02 times 10 to the 23rd copper atoms over 1 mole. Moles cancel, and you end up with 3.0 times 10 to the 23rd atoms of copper. If I'm going the other direction, converting atoms to moles, let's say I want to know how many moles of vanadium are in 2.5 times 10 to the 24th atoms of vanadium. I take 2.5 times 10 to the 24th atoms of vanadium times the conversion factor, 1 mole of vanadium over 6.02 times 10 to the 23rd atoms. Comes out to 4.15 moles of vanadium. One word of caution here. When you use your calculators and you divide by 6.02 times 10 to the 23rd, you should always put the 6.02 times 10 to the 23rd scientific notation number in parentheses. Testing 1, 2, 3. How many atoms of carbon are in 2.65 moles? How many moles of silicon are in 2.44 times 10 to the 25 atoms? How many iron atoms are in 3.4 moles of iron? Set these up. Take the 2.65 moles of carbon times 6.02 times 10 to the 23rd atoms over 1 mole. Take the 2.44 times 10 to the 25th atoms of silicon times 1 mole over 6.02 times 10 to the 23rd atoms. Don't forget to put the scientific notation in parentheses. And lastly, take the 3.4 moles of iron times 6.02 times 10 to the 23rd atoms over 1 mole. Do your work, and you should have gotten these 3 answers. Molar mass. Molar mass allows us to count atoms by weighing. Molar mass is the mass of 1 mole of an element or compound. Molar mass is actually the same as the atomic mass, but we actually use atomic mass in AMU units. The molar mass simply uses the same number, but grams. So a mole of silver, 107.9 grams. A mole of carbon, 12.01 grams. A mole of sulfur, 32.07 grams. So that's telling me that 6.02 times 10 to the 23rd atoms of silver have a mass of 107.9 grams. If we put atoms together to make a chemical formula, whether it be a molecule or a formula unit, we sum the molar masses of the atoms in the formula to get the molar mass of the compound. For example, if I wanted to calculate the molar mass of calcium chloride, in other words, what is the grams of mass for a mole of calcium chloride formula unit, 6.02 times 10 to the 23rd CaCl2s. Looking at the chemical formula, I see that calcium has 1 mole in the formula, chlorine has 2, subscript of 2, so 1 mole of calcium weighs 40.1 grams, 1 mole of chlorine weighs 35.5 grams, so 2 moles of chlorine weigh 71.0 grams. 40.1 plus 71.0 is 111.1 grams for calcium chloride. More practice. Let's calculate the molar mass of K3PO4. Just a minute. Mole of K2CrO4 would weigh 294.2 grams. Finally, C12H22O11 is the formula of table sugar, sucrose. There are 43 atoms in the formula, 45 atoms in the formula rather, and 45 atoms takes up a lot more space than just 1 atom, so we see our sucrose taking up a lot more space than sulfur, but it's 342.2 grams of sucrose in a mole. Practice doing molar masses. K2O, we need to take 2 times potassium's molar mass of 39.1 plus 1 times oxygen's molar mass of 16. In letter B, we have 1 aluminum atom, so we look up aluminum on the periodic table. We have 3 oxygens and 3 hydrogens. When you add up all those atomic masses off the periodic table, here we have K2O, 2 times 39.1 is 78.2. 1 times 16 is 16, so that's a total of 94.2 grams. So a mole of K2O is 94.2 grams. ALOH3, a mole of that would be 78 grams. You have 1 mole of aluminum with a molar mass of 27. 3 moles of oxygen times 16 is 48. 3 moles of hydrogen times 1.01 is 3.03. These molar masses can be used as conversion factors. We write the conversion factor from the molar mass. It relates the grams to the moles. You notice the unit was grams per mole. So for example, let's write the molar mass factors for methane. Methane's used in natural gas for stoves and heaters. Molar mass of methane, CH4, would be 12.0 plus 4 times 1.0 is 16.0. So you have two conversion factors. You could use 16.0 grams over 1 mole or 1 mole over 16.0 grams as a conversion factor, depending on whether you want to change from grams to moles or moles to grams. Let's try one. Allyl sulfide, C6H10S, is a compound that has the odor of garlic. How many moles of C6H10S are in 225 grams? So our solution to this is to first calculate the molar mass of C6H10S. So that's 6 times 12.0 for carbon, 10 times 1.01 for hydrogen, 1 times 32.1 for sulfur, for a total of 114.2 grams per mole. Then we set up our calculation using a mole factor. Remember, we had 225 grams of allyl sulfide, so we're going to multiply that by 1 mole of allyl sulfide over 114.2 grams. 225 times 1 divided by 114.2 is 1.97 moles of C6H10S. Notice the conversion factor was simply 114.2 grams per mole flipped or inverted. Take the reciprocal of it to get 1 mole over 114.2 grams. Final answer, 1.97 moles of C6H10S. Let's use cars to discuss the mole-mole ratio that you can get from a chemical formula. How many cars are in a mole of cars? Well, of course, it'd be 6.02 times 10 to the 23rd. But a car is a chassis with 4 wheels. How many tires are in 1 mole of cars? If I have 6.02 times 10 to the 23rd, I obviously have more tires than I have cars, because there are 4 tires for every car. So it would be 4 times 6.02 times 10 to the 23rd, or 2.41 times 10 to the 24th tires in 1 mole of cars. So in the same way, how many moles of oxygen are in 1 mole of carbon dioxide? Since there are 2 oxygens in the carbon dioxide formula, 1 mole of carbon dioxide would actually contain 2 moles of oxygen atoms. And just for kicks, 1 mole of carbon atoms. So the subscripts in a formula show the relationship of how many atoms are in that formula. And so if you want to know the moles of atoms of each element in a mole of compounds, you can use those subscripts as conversion factors. This picture is a picture of the molecule glucose, which is C6H12O6. In 1 molecule of glucose, there are 6 atoms of carbon and 12 atoms of hydrogen and 6 atoms of oxygen. In 1 mole of glucose, there are 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen atoms. So the subscripts can be used to write conversion factors. The conversion factors are going to give us the moles of each element in 1 mole of compound. For aspirin, C9H8O4, you can write the following conversion factors. 9 moles of carbon over 1 mole of C9H8O4, 8 moles of hydrogen over 1 mole of C9H8O4, or 4 moles of oxygen over 1 mole of C9H8O4. Or you can invert those conversion factors and make more conversion factors. 1 mole of aspirin over 9 moles of carbon, 1 mole of aspirin over 8 moles of hydrogen, or 1 mole of aspirin over 4 moles of oxygen. All of these are legitimate conversion factors because they give us how many moles of atoms are in a mole of the compound. So show me the money. Show me you can do this. How many moles of oxygen are in 0.150 moles of aspirin? You're going to take 0.150 moles times 4 moles of oxygen atoms over 1 mole of aspirin. How many oxygen atoms are in 0.150 moles of aspirin? You're going to take your answer from A and convert moles of oxygen to atoms using the conversion factor 6.02 times 10 to the 23rd atoms over 1 mole. So here's the conversion for moles of oxygen atoms. 0.600 moles of O. Here's the conversion factor for moles of oxygen atoms converted to actual atoms. So notice you've added on the extra conversion factor at the end of 6.02 times 10 to the 23rd oxygen atoms over 1 mole. So 0.6 moles of oxygen is 3.61 times 10 to the 23rd oxygen atoms. We think about one of the major fundamental laws of chemistry, the conservation of matter. The law of conservation of matter indicates that in any ordinary chemical reaction, matter cannot be created nor destroyed. So there's no change in total mass that occurs in a reaction. The mass of the products is equal to the mass of the reactants. As a result, a chemical equation or a chemical reaction represented by an equation must show that no matter is created or destroyed. In other words, that all the parts that were in the original reactant side must still be in the product side. Chemical reaction doesn't change atoms to new atoms, it just or get rid of any atoms or make any atoms. It simply rearranges the atoms. That's why the mass doesn't change. Here we have, Houston, we have a problem. What if we were to have to make a cake? And the recipe says that 2 eggs and 1 cup of water and 1 box of cake mix makes a cake. I could write a chemical equation for that. I could say 2 eggs plus 1 water plus 1 cake mix yields 1 cake. But what if we only had 1 egg? I'd have to cut the cake mix in half, wouldn't I? Instead of using 2 eggs, I would use 1/2 times 2 eggs, which is 1 egg. Instead of using 1 cup of water, I'd use half a cup of water. Instead of using the entire box of cake mix, I would use half of the box of cake mix. I wouldn't get a cake, I'd get half a cake in the end. But notice that with this recipe, you can alter the recipe. You can cut it in half, you can double it, you can triple it if you have a lot of people to feed. These recipes, these chemical equations, have particular ratios to them, but you can multiply those ratios by whole numbers and get other ratios that work. Consider the following equation. 4 iron atoms and 3 oxygen atoms yield 2 Fe2O3 formula units, or we could read the equation as moles by placing the word moles between each coefficient and formula. 4 moles of iron plus 3 moles of oxygen yield 2 moles of iron oxide. These coefficients, 4, 3, and 2, become mole-mole factors that can be used as factor label conversion factors. For example, the factors for Fe and O2 are 4 moles of iron for every 3 moles of oxygen. Or if you flip it, 3 moles of oxygen for every 4 moles of iron. The ratio for iron to iron oxide is 4 to 2. 4 moles of iron for every 2 moles of iron oxide, or inversely 2 moles of iron oxide for every 4 moles of iron. I want the oxygen to iron oxide ratio. It's 3 moles of O2 for every 2 moles of Fe2O3, or 2 moles of Fe2O3 for every 3 moles of oxygen. So these factors can be used to convert moles of one chemical in a formula equation to moles of another chemical. For example, if I wanted to know how many moles of iron oxide can form from 6 moles of oxygen, I would use the relationship that 3 moles of oxygen can make 2 moles of iron oxide. And then I would write a mole-mole factor to determine the moles of iron oxide. I'd take 6 moles of oxygen times 2 moles of iron oxide over 3 moles of oxygen. So 6 times 2 divided by 3 is 4 moles of iron oxide. 4 moles of iron oxide can form from 6 moles of oxygen. Let's try another one here. How many moles of iron are needed for the reaction of 12 moles of oxygen? Well, 4 Fe plus 3 O2 yields 2 Fe2O3, so 12 moles of O2 times 4 moles of iron over 3 moles of oxygen. Notice I'm using the coefficients as mole-mole ratios, mole-mole conversion factors. 12 times 4 is 48 divided by 3 is 16 moles of iron. 16 moles of iron are needed for the reaction of 12 moles of oxygen.